Hello, I'm Mr. McBrien. This is TEJ2O, hexadecimal numbers. As we discussed yesterday, the Ontario curriculum suggests that students should have an understanding of binary and hexadecimal numbers. We'll cover the hexadecimal numbers part today. Now, a lot about hexadecimal numbers will seem strange again, not unlike the binary case. Hex numbers really aren't a natural counting base for us as 10-figured human beings. However, it does pop up a lot, mostly because of the properties of the number 16. It's an exact square. It's also 2 to the 4. There are some cute tricks about 16. The first 4 odd numbers added are total up to 16. A compass rose is divided into 16 points. Chessboards have 16 black and 16 white pieces. We talked about transistors and how computers store and manipulate data in binary base 2 numbers. Now, early computers wrote programs or had programs written exclusively in binary, and programming was a beastly task. And the reason why is because it was really easy to put errors into your code. The human eye just isn't designed to differentiate between a whole series of different closely related objects. So once we start putting a lot of them in together in arrays, they all just sort of blend into one, and it makes it really hard for us to read them. Now, similarly, we have trouble looking at screens full of binary numbers. We can't really read them. We had to find a way, an efficient way, for early computers to convert large binary numbers to something humans could read and manipulate. Now, we've already seen that converting binary numbers to base 10 requires some processing power. And early computers really didn't have the kind of processing power necessary to be able to do that kind of thing. They couldn't waste the effort on this. And so instead of converting to base 10, for a human to look at these numbers, these early computers used base 16. And we'll see soon, in the next few slides, how it's much easier to convert between base 2 and base 16. But first we have to gain some understanding of hexadecimal numbers. Now, you can buy widgets to convert between these numbers. You can use websites, of course, to do conversions. We need to, though, gain an understanding of the basis of these things, and that's what we'll do now. And we'll do it using the same kind of number table we used in the binary case. I mentioned earlier that those tables we used can apply to any number system. Well, they apply to binary, they apply to decimal, and they can apply to hexadecimal as well. So, similar to our 10 to the 0, 10 to the 1, 10 to the 2, if we want to have hexadecimal, we have 16 to the 0, 16 to the 1, 16 to the 2, 16 to the 3, 16 to the 4. The numbers get big fast. So we have our 1s. Of course, we have to be able to represent 1s. Instead of 10s, the second column represents 16s. And instead of hundreds, the third column represents 256s. And if we grasp this table, and you should certainly be able to reproduce this table for any tests, if we grasp it, we can convert between hex and decimal very easily. Now, the challenge, though, comes with the fact that we only have 10 digits. What do we do when we go up past 10? And the answer is, we could have defined a new kind of squiggle that would have represented a 10 and a new one that represented an 11. We certainly couldn't have used 1, 0 because we'll need this, as we'll see in a second. So we needed some new kind of shape. We could have used a square and a circle and these things. But instead, because we already had the capacity to represent these on the screen, we decided to use A, B, C, D, E, F to represent 10, 11, 12, 13, 14, and 15. And so these are the additional 6 numbers that we need to have hexadecimal number representation. And these numbers, you've likely seen these before on the screen and weren't really sure what you were seeing. For example, we can have the number FFCCCC or 99FF66. And these things, these are hexadecimal numbers shown on the screen. And there are lots more examples we can see of hexadecimal numbers. And often when we do see them, we're not all that pleased to see them. Okay, converting binary to hex is really very simple. And the reason for this is that the numbers 4 and 16 are closely related. We can take binary numbers and divide them from right to left into what's called nibbles, into groups of 4. And when we do this, notice that the largest number we can represent here with this group of 4 is 1, 1, 1, 1. 8, 4, 2, 1. Add them together, we get 15. That's very convenient because that's the largest number we can represent with a single hexadecimal digit. And for this reason, we can convert these nibbles individually into hexadecimal digits and convert from binary to hex very simply. We break the number into 4-digit nibbles and then convert each one of these to a hex number, and we convert a 16-digit binary number into a 4-digit hex number by doing 4 operations. So since each nibble can only hold a value of between 0 and 15, we can replace each nibble with the equivalent hex number. So 1011 becomes A, 11 becomes 3, 1110 becomes E, and 1011 becomes 9. And so, converting this long 16-digit binary number to hex is 9E3A. Now it'll also work the opposite way around. What we can do is we can take each hex digit and convert it into 4 binary ones, convert it into a nibble. And so here's an example of a huge problem here, which if we were converting to decimal would require a great deal of time. But in fact, with a little bit of practice, we can do these conversions very fast. So this 1, 2, 3, 4, 8-digit hex number becomes a 32-digit binary number by converting B to 1011, 1 to 1, 0 to 0, A to 1010, 4 to 0100, and so on. An 8-digit hex number has become a 32-digit binary number. Now sometimes we have to convert directly from decimal to hex or vice versa. And when we do that, we use the exact same process we use with binary conversion, just using our updated table. So here's our hex table with our numbers here. When we're presented with a number such as 5F7B, we can then just do the multiplication. This number, this 4-digit hex number, has B 1s, 7 16s, F 256s, and 5 4096s. We multiply and then add them out. So 5 times 4096 is 20,480. 15, or F, times 256 is 3840. 7 times 16 is 112. And 11 times 1 is 11. And we add these together, and 5F7B in hex is the same as 24,443 in decimal. Now, you could involve binary in this, but there's no real efficiency to doing so. So you could first switch to binary if you found this more efficient. Really, I don't see any reason why this is more efficient than simply going directly there. But this does point out a few little nomenclature things that we should mention. Typically, hexadecimal numbers have a small h after them. Binary numbers often have this subscript 2 after them. And in most cases, we take base 10 as implied, but if we did want to say that a number was a base 10 and make it explicit, we would put a subscript 10 afterwards. So, something to keep in mind, hexadecimal numbers are virtually never stored inside a computer. Everything's stored in binary. This is a conversion that the system does in order to communicate with humans. It is worthwhile keeping this in mind. Okay, so you can try the problem FACE, base 16, or it could have been a small h afterwards, in binary. Hopefully you'll get this number. Now what about this problem? This binary number in hex. Go ahead and give it a shot. Pause it if you like before you do it. You should get 5ODOFF. So to summarize, though computers store and manipulate values in binary, they usually display them in hexadecimal format. Each group of 4 bits, a nibble, represents one hexadecimal digit. Hexadecimal digits run from 0 to 9, and then A to F to manage to go from 0 to 15, in essence. The value of each hex digit rises by a power of 16 as the columns move to left to right, just like the other tables we've seen. And you can denote a hexadecimal value by following a number with a lowercase h or a small subscript 16. For your homework, please work through the hexadecimal workbook from Google Classroom. When you're finished, you should have a pretty good grasp of hexadecimal numbers. Thanks, and have a great day.